Hello friends, in this video we are going to study how to determine the capacity outage probability rate. So let us study it in detail. So if we consider the loss of load approach, then the generator model which is required for the loss of load approach is sometimes also known as capacity outage probability table. So as the name suggests, it is simply an array of capacity levels and the associated probabilities of its existence. So if all the units in the system are considered to be identical, then the capacity outage probability table can easily obtained by using the binomial distribution. Now it is extremely unlikely, however, that all the units in a practical system will be identical, and therefore the binomial distribution is the limited application. Now if we consider the system, then it is not necessary that all the units will be identical. There might be some differences. Hence the use of the binomial distribution system is not adequate. So the units can be combined using the basic probability concepts, and this approach can be extended to simple but powerful recursive technique in which units are added sequentially to produce the final model. So if we consider the recursive technique, then in this technique we can utilize the unit which are having the same values as well as different values. So this concept can be illustrated by the use of the simple example as shown below. So a system consists of two 3 megawatt units and one 5 megawatt unit, and it has the force outage rate, that is FOR, of 0.02. Also the two identical units can be combined to give the capacity outage probability table as shown below. So table 1 shows the capacity outage probability table. Here there are two columns. First column is for the capacity out of service and second column is for the probability. So if we consider for the 0 megawatt, then the probability is 0.9604. Similarly for 3 megawatt, the probability is 0.0392. Then for 6 megawatt, the probability is 0.004. The addition of the probability is 1. We know that whatever be the values of the individual probabilities, but addition of all the probabilities should be equal to 1. Now a system consists of two 3 megawatt unit and one 5 megawatt unit which is having the force outage rate of 0.02. So the two identical units were as shown in table 1. Now the 5 megawatt generating unit can be added to this table by considering that it can exist in two states. So it can be of the service with the probability of 1 minus 0.02, that is nothing but 0.98, or it can be out of service with the probability of 0.02. So here two conditions can be considered, in service and out of service. So the two resulting tables, that is table 2 and table 3, are therefore conditional depending upon the assumed state of the unit. So whether it is in service or out of service, depending on this there are two tables. So this approach can be extended for any number of unit states. So this is the table for the 5 megawatt unit which is in service. So again there are two columns, capacity out and probability. So for 0 plus 0, that is 0 megawatt, the probability is 0.9604 multiplied by 0.98, which is equal to 0.941192. Similarly, if we consider 3 plus 0, that is 3 megawatt, then the probability is 0.0392 multiplied by 0.98, which is equal to 0.038416. Similarly, for 6 plus 0, that is 6 megawatt, probability is 0.0004 multiplied by 0.98, which is equal to 0.000392. The addition of all the probabilities 0.98. So this is in case of unit which is in service. So we have already seen for the unit in service the probability should be 0.98. So this condition is satisfied by the table. Now let us consider the table for the 5 megawatt out of service. Again here there are two columns. One is for the capacity out and second is for the probability. Now we have already seen that the probability for the out of service should be 0.02. So let us see if this condition is satisfied. Now for the first unit, that is 0 plus 5, that is 5 megawatt. The probability is given by 0.9604 multiplied by 0.02, which is equal to 0.019208. Similarly, if we consider the second unit, then the capacity is 3 plus 5, that is 8 megawatt, and the probability is 0.0392 multiplied by 0.02, which is equal to 0.000784. Now the third unit is 6 plus 5, that is 11 megawatt, and the probability is 0.0004 multiplied by 0.02, which is equal to 0.000008. So if we add all the probabilities, then we get addition to be 0.02. Hence the condition is satisfied. Now the two tables can now be combined and reordered in order to form the table number 4. So the probability value in the table is the probability of exactly the indicated amount of the capacity being out of service. Now an additional column can be added which gives the cumulative probability. So this is the probability of finding a quantity of capacity on the outage which is equal to or greater than the indicated amount. So this is the table which shows the capacity outage probability for the 3-unit system. Now here there are 3 columns. First column is for the capacity out of service. Then second column is for the individual probability. And the third column is for the cumulative probability. Now if we see here, for the first, that is 0, the probability is 0.941192. Whereas the cumulative probability is 1. Next, for the second stage, that is of the 3 megawatt, the individual probability is 0.038416, whereas the cumulative probability is 0.058808. Then for the next unit, that is of the 5 megawatt, the individual probability is 0.019208, whereas the cumulative probability is 0.020392. Similarly, for the fourth unit, that is of the 6 megawatt, the individual probability is 0.019208, whereas the cumulative probability is 0.001184. Now if we consider the next unit having the 8 megawatt capacity, the individual probability is 0.000784, whereas the cumulative probability is 0.000792. If we consider the next unit having the 11 megawatt, then the individual probability is 0.00784, whereas the cumulative probability is 8 multiplied by 10 raised to minus 6. So if we do the addition of the individual probability, it is equal to 1. So the cumulative probability values decrease as the capacity on the outage increases. Although this is not completely true for the individual probability table, the same general trend is always followed. For instance, in the above table, the probability of losing 8 megawatt is higher than that of the probability of losing 6 megawatt. In each case, only 2 units are involved. Now this difference is due to the fact that in 8 megawatt case, the 3 megawatt loss contribution can occur in 2 ways. So if we consider the practical system, then the probability of having a large quantity of the capacity forced out of service is usually quite small, as this condition requires the outage of several units. Theoretically, the capacity outage probability table incorporates all the system capacity. Now this table can be truncated by omitting all capacity outages for which the cumulative probability is less than the specified amount. Let us consider it as 10 raised to minus 8. This also results in a considerable saving in the computer time, as this table is truncated progressively with each unit addition. So the capacity outage probabilities can be summed as units are added or calculated directly as the cumulative values, and therefore no error need results from the truncation process. Now if we consider the practical system, which consists of large number of units of the different capacities, the table will contain several hundreds of the possible discrete capacity outage levels. But these numbers can be reduced by grouping the units into the identical capacity groups prior to combining them, or by rounding the table to the discrete levels after combining. So unit grouping prior to the building the table will introduce unnecessary approximations which can be avoided by the rounding of table approach. So the capacity rounding increment used depends upon the accuracy which is desired. Also, the final rounded table contains capacity outage magnitudes that are multiples of the rounding increments. Now the number of the capacity levels decreased as the rounding increment increases, with a corresponding decrease in the accuracy. So the procedure for the rounding of a table is shown in the following example. Consider that two 3 megawatt units and one 5 megawatt unit, which is having the forced outage rate of 0.02, were combined to form a generation model as shown in table 4. Now this table, when rounded at the 5 megawatt increment, will contain only the capacity outage magnitudes of 0, 5, 10 and 15 megawatt. So the rounded table is obtained as shown in table 5. So this is the rounded table. Here there are two columns. First is capacity on outage megawatt and second is the individual probability. So if we see for 0 megawatt, the individual probability is calculated as 0.941192 plus 2 divided by 5 multiplied by 0.038416. So the answer is 0.9565584. Similarly, the next unit is of 5 megawatt. So the probability can be calculated as 0.019208 plus 3 by 5 multiplied by 0.038416 plus 4 by 5 multiplied by 0.000392 plus 2 by 5 multiplied by 0.000784. So the answer is 0.0428848. Similarly, for the next unit having the capacity of 10 megawatt, the probability can be calculated as 1 by 5 multiplied by 0.000392 plus 3 by 5 multiplied by 0.000784 plus 4 by 5 multiplied by 8 into 10 raised to minus 6. So the answer is 0.000552. Now the next unit is having the capacity of 15 megawatt. So the probability for the 15 megawatt unit can be calculated as 1 by 5 multiplied by 8 multiplied by 10 raised to minus 8. 1 by 5 multiplied by 8 multiplied by 10 raised to minus 6, which is equal to 0.0000016. So if we add all the probabilities, we will get the answer as 1. So in order to rounding of this process, the general expression can be written as P of Ci is equal to Ck minus Ci divided by Ck minus Ci multiplied by probability of Ci, and the probability of Ck is equal to Ci minus Ci divided by Ck minus Ci into probability of Ci. For all states I falling between the required rounding state j and k. So the use of the rounded table is combination with the load model to calculate the risk level introduces certain inaccuracies. Now the error depends upon rounding increment used and the on slope of the load characteristic. So the error can be decreased with increasing the slope of the load characteristic, and for a given load characteristic the error increases with the increased rounding increment. So both these things are interrelated. So the rounding increment used should be related to the system size as well as composition. Also, the first non-zero capacity on outage stage should not be less than the capacity of the smallest unit. The generation system model in the form as shown in table 4 can be used to illustrate the basic inadequacies of the conventional deterministic approaches to the capacity evaluation. So in this way we have studied the capacity outage probability rate. Thank you friends for watching this video. Stay tuned with Ekeeda and do subscribe our channel Ekeeda. Thank you.